Okay, sorry about that. Obviously, this is the part of the semester for technical problems. Okay, so let's just one very quick announcement. So William is going to be recovering for a number of weeks, and so we have a new GSI. Do you want to stand up for a second? So Sierra is going to take on William's role for us for the the next few weeks, essentially. So if you were on William's list, if you were assigned to William, then Sierra is going to be the William stand-in for a number of weeks. So please, I haven't done it yet. I will post her email address on the class webpage. We'll send out an email to everybody with Sierra's email, just saying the same thing. And so if you have questions, rather than sending them to William, please direct them to Sierra. Okay. All right. So on Thursday we started talking about how we interpret the wiggles, and we talked about P waves and S waves, and so we're going to kind of continue right where we left off and sort of start exploring more how we can actually use these wiggles to tell us about the earthquake process. Okay, so we're going to use this earthquake. I'm going to show you some data, rather, from this particular earthquake. This was a big earthquake in Pakistan a number of years ago. So the earthquake epicenter is right here. And then I'm going to show you data from station GNI, and then Berkeley, of course, is all the way over here. I'm not going to show you data from Berkeley, but I'm going to show you some data from station GNI, which is in Turkey, right here. And so this was a very significant earthquake. 80,000 people were estimated killed in this particular earthquake, and you can see the reason for the very high number of fatalities in this photo here. So essentially, the buildings were not earthquake resistant in any way, and essentially the buildings they're sort of these concrete buildings that just pancaked during the course of the earthquake, and of course that leads to a very high number of fatalities. Okay, so my first question is, how long do you think it takes for the seismic waves to get from Pakistan to easternmost Turkey? Just guess. 7 seconds, 30 minutes, 2 minutes, 3 minutes, 1 minute, 5 minutes. All right, I think we pretty much got it covered. 45 minutes. All right. Okay, so this is how long it takes for the data to actually get to the station. So this is the vertical component seismograph recorded at GNI for that particular station. Okay, so this is just the amplitude of the shaking. That's what the wiggles represent at this station, obviously. And then this is time. Okay, and so this is 400 seconds, 600 seconds. So this is 300 seconds right here. Okay, so the P wave arrives a little bit more than 300 seconds after the origin time of the earthquake. So a little more than 5 minutes after the origin time of the earthquake. Okay, so that's how long it takes for seismic waves, P waves, to get from here over here is about 5 minutes. All right. And then this is the S wave arrival. Okay, so this is just a vertical component seismogram. So when we did the little demonstration on Thursday, of course, I showed you that P waves, the energy is going in this direction, P waves is a vibration in this direction, and S waves are a vibration in this direction. And so you can use the seismogram, the three components, I'm going to show you that in a moment, to determine the P and S wave. So we'll get to that. But what I just want you to recognize now is that the P wave arrives after about 300 seconds, and in round numbers, the S wave arrives after about 600 seconds. Okay, so a very rough rule of thumb is it takes about twice as long for the S wave to arrive as the P wave. Okay? And now what is key in that statement is, of course, how long it takes for the P wave to arrive depends on how far you are from the earthquake, obviously. If you're very close to the earthquake, the P wave is going to arrive very quickly, and as you get further and further away, all the way around to the other side of the globe, because remember, we use global seismic networks to detect earthquakes around the globe, then the arrival time of the P wave gets later and later. Okay? And likewise, the arrival time of the S wave gets later and later, because the S wave takes about twice as long as the P wave. All right? So it turns out that the difference between the P wave and the S wave varies as a function of distance from the earthquake. So just to illustrate that, here's another seismogram. This is for a different earthquake. But this is another seismogram. This is a seismogram recorded at Berkeley for a magnitude 5.3 earthquake that was in close to Santa Cruz. Okay, so a relatively local earthquake, similar to the Loma Prieta. This isn't the Loma Prieta, but it's sort of a similar geometry or similar location to the Loma Prieta earthquake in the mountains north of Santa Cruz. And here you can see the P wave arrival, and you can see the S wave arrival, and you can see that the difference in the arrival time between the P and S is perhaps about 12 seconds. Okay? So there's a 12-second difference here, and there's a sort of 300-second difference for this earthquake. And this difference in the time is all related to how far the earthquake is away from the station, and that, of course, is how we're going to locate earthquakes. Because when you're trying to locate an earthquake, of course, you don't know when the earthquake occurred, you just know when the P wave arrived and when the S wave arrived. And you then have to determine when it occurred and also where it was located. But before I show you that, let me show you the three components for this seismogram. So this is the same vertical component. I've actually filtered it to detail, don't worry about it. This is the same vertical component that I just showed you, so that you're just seeing the lower frequency energy, the longer wavelength wiggles. And this is the vertical component, this is the east-west component, and this is the north-south component. Okay? And so when it comes to identifying the P wave and the S wave, what's the difference between the two? What can we see from looking at these three seismograms? For which? So the S wave has more intense shaking. The amplitude of the S wave is bigger than the P wave. That's typical. That's correct. Okay, so the height of these wiggles are bigger than the height of these wiggles. What else? Yeah. That's right. So the amplitude of the P wave is larger on the vertical than it is on the two horizontals. Okay? And the amplitude of the S wave is actually larger on the horizontals than it is on the vertical. It's not as easy to see that with the S wave in this particular case, but the S wave is always larger on the horizontals, and the P wave is always larger on the vertical. Exactly. Those are the two key observations. Those are the two key characteristics of the P wave and the S wave. And of course, the reason for this is pretty straightforward. So, find a piece of blackboard. So remember that this is a some chalk. So remember that this is an arrival that is about there's some significant distance away from the earthquake. So this is the entire globe. Okay, you can think of the earthquake as being in Pakistan over here, and you can think of the seismic station as being up here. The actual path that the seismic waves take dives down into the Earth's interior and then comes up to the station. The point is that when you're looking at seismic waveforms that have been recorded some distance away from the epicenter, the seismic energy is traveling almost vertically up. So what's the direction of the particle motion for the P wave? Up, right? The direction of particle motion is in the same direction that the energy is traveling. So a P wave is going to have motion that is going in this orientation, so it's going to be up-down when it gets to the station. Okay, so that's why the P wave is strongest on the vertical component. And then the S wave, what's the orientation of the particle motion? Right, it's perpendicular to the path. This is the path, and so perpendicular direction is like so. And because this path is vertical, the S wave is primarily on the horizontal component. Does everybody see that? Good to be able to get your head around this geometry so you can kind of understand the wiggles that you are seeing. Okay, any questions? Yeah. Oh, I'm sorry. So the big circle is the Earth. Okay, so this, I'm sorry, yes, I'm so used to drawing this diagram. So this is a cross-section through the Earth as a whole. So this is the center of the Earth, this is the surface of the Earth, this is the earthquake in Pakistan, close to the surface of the Earth. And then this is the station at GNI, which of course is at the surface of the Earth, okay? And then this just shows the ray path diving down into the Earth's interior and then coming back up to the station. That's the shape of the path that the energy takes, the seismic waves. Exactly. So it starts here. You can think that with time, this is the ray path. This is the path that the energy takes to this point. But what's actually happening, of course, is that the energy is radiating out like this. So the energy from this earthquake is radiating out. It travels through the globe, and we're just looking at the energy that gets to that one particular station. Okay? Other questions? All right. So that's P waves and S waves and what they look like on the seismograms. Okay. And so then, right. So again, just to reiterate, the time that we measure here is the S minus P time, the arrival time of the S, minus the arrival time of the P wave. Yeah. Okay. So I'll come back to that question later in the lecture. Good question. Okay. So here's some more seismograms. They've been rotated on their side just to confuse you. And so this now shows time going up in this direction. Okay? And these seismograms have been plotted as a function of the distance from the earthquake. Okay? And to confuse you even more, distance is measured in degrees, right? Not kilometers. So why is distance measured in degrees? It's actually very straightforward. So here's the center of the Earth. So when we measure distance in degrees, we're measuring the distance of a seismic station from the epicenter of the earthquake. What we're doing is we're actually measuring this angle. Okay? So this particular, as I've drawn it here, this particular station is at an epicentral distance of, I don't know, say 70 degrees. Right? Obviously, a station that's here would be at 90 degrees. A station that's on the opposite side of the Earth would be at 180 degrees. Okay? So we're just measuring distance in terms of this angular distance inside the globe. All right? So 180 degrees is, you can't get further than that, obviously, from a station. So that's why we go from 0 to 180 degrees. And then, of course, the station, the data that's furthest away at 140 degrees has the arrival latest in the seismogram, and the one that's closest has the arrival closest. You can also see that the total seismic wave train is extending out as you get further and further away. All of the energy, all of the packet of energy all arrives in this little packet here. But let's pick a good one. If you go to this blue one here, you can see that, well, the P wave actually arrives all the way down here, and then the S wave, and then the surface wave. So it's spreading out the packet of energy. Okay? So obviously the S minus the P time increases as a function of distance away from the earthquake, and that's how we're going to locate these earthquakes. Questions? All right. Okay, so the way that we locate the earthquakes is, of course, we just have a seismogram. Remember that you're an observer now, so you just have a seismogram at one station to start with. And this is what that seismogram might look like. So remember, of course, the seismograms are very sensitive, so they're recording the background noise all of the time. And then an earthquake occurs, the P wave arrives, and then the S wave arrives. And so we measure this S minus the P time. Now, if we want to locate the earthquake, of course, we need, well, what we actually need is a total of 4 things. We need the latitude, the longitude, the depth of the earthquake, and then, of course, we have to solve for the origin time of the earthquake. We don't know what time the earthquake occurred, so we have to solve for that as well. Now, you can make this a much simpler problem by pretending that the Earth is flat, right? Treat it as a 2D problem, in which case we would only be trying to understand the latitude, or determine rather, the latitude and the longitude of the earthquake, and then the origin time of the earthquake. So I'm going to run through how we do that, as it's a simpler case. So here's more seismograms plotted just like that as one that I showed you a moment ago, vertically, as a function of distance from the epicenter, this time shown in kilometers. So we have one station that is very close, relatively close to the event, about 1,500 kilometers away, and it shows the P wave arrival and it shows the S wave arrival. And so there is a 3-minute interval between the P wave arrival and the S wave arrival at 1,500 kilometers. Okay? You go to this seismogram, it's further away, there's an 8-minute interval, and in this seismogram even further away, there's an 11-minute interval. Right? So the way that you would determine the location of the event is the first thing you do is you measure the S minus P time. Of course, you don't know how far the station is from the event because we don't know where the event was yet. But you can measure the S minus P time, and of course you can tell which one is closest and which one is furthest away just based on how big the S minus the P time is. Okay? And so now, I'm sorry, okay. So we measure the S minus the P time on the seismogram. Now, based on the S minus P time, we can come to this plot that has the theoretical P wave arrival time and the theoretical S wave arrival time. So having measured 3 minutes on our seismogram, we can then look for the place on this plot where the S and the P arrival are 3 minutes apart. Okay? So we measure our 3 minutes, we come to this plot, we find that this is the place, this is the distance where the S and the P are 3 minutes apart, and we can determine that this station is therefore at 1,500 kilometers from the earthquake. All right? And we go to our second seismogram and we measure the S minus P time, and it's 8 minutes. We come to this plot and we find that this is the distance, about 5,500 kilometers, is where the difference is 8 minutes. Right? So on and so forth. So we do this for all of our seismograms, and now based on the S minus P time, we know how far each of the stations is from the epicenter of the earthquake. Okay? And then, if we're doing a 2D problem, you simply get out a big piece of paper, and you get out a compass, and you start to draw circles at these distances from stations. So we have station 1. This is a different example, but it's 200 kilometers. No, is it the same? No, it's different. So station 1, the seismogram is 2,000 kilometers away, and so you draw a circle that's at 2,000 kilometers. And now we know that the earthquake occurred somewhere on this blue circle. All right? You then go to the second closest station, that turns out was 4,000 kilometers away, and you draw a circle at 4,000 kilometers. And so the blue and the pink circles intersect at 2 points, here and here. So we know that the earthquake was either located here, or it was located over here. And then we go to our third station, and we know that was at 6,000 kilometers. We draw a third circle, and lo and behold, they all intersect at 1 point. And so this is obviously the location of the earthquake. All right? It's pretty straightforward, right? So that's how you would locate the origin of the earthquake. Of course, this is a very simple geometric problem because we're doing it in 2 dimensions, and also because there are no errors. When it comes to doing it in the real Earth, of course, we have to solve the 3D problem, and also there are always errors in our measurements. And so you inevitably end up with a sort of broad blob-like region where the event could be located, and you have to you determine the best fitting location for the earthquake, i.e. the point in the Earth's 3D structure where if you place the earthquake at that location, you minimize the errors for all of the observations. Okay, but that's a technical detail. This is the concept of how we locate earthquakes. Any questions? Yeah. Okay, so the way you determine the distances, right, so when we're doing this, we know that this station is 2,000 kilometers, we know this station is 4,000 kilometers. How we determine those distances is from this figure. So we look at our raw seismogram and we just measure the S minus P time. And we determine that S minus P time is, let's say, 3 minutes. We then come to this plot, so remove these seismograms, just pretend you have the blue and the red line, and we find the distance where the S and the P arrival are 3 minutes apart. Of course, there's only one place on this plot where the S and the P arrival are 3 minutes apart. So we find that, and that happens to be right here, and that tells us, in this case, that it's at 1,500 kilometers. Exactly. So this is not great because these 2 slides obviously come from different explanations, right? So this will tell us that the first station is 1,500 kilometers away, the second station is 5,500, and the third station is 8,500. Okay, in this case, it's a different case. We have a station of 2,000, 4,000, 6,000. Okay, but it's obviously the same principle. Did that answer your question? Yeah.
Those lines,
Yeah, great question. How do we know that it looks like this? And the answer to that is that is simply from basically understanding the overall global structures. Over time, of course, it seems like a simple problem now, but to start with, we had no idea how to do this. And so people would just measure the difference in these arrivals. And over time, we've sort of begun to understand what the Earth structure looked like. And so we now can predict what these arrivals should be based on a 1D Earth model, an Earth model where we only allow the velocity to vary as a function of radius. And so that we can then predict these arrivals. So just having this figure is the result of many years' worth of research. Yeah. Why is this the distance? Yeah, no. So what we're doing is, so this plot is showing us, so this is the elapsed time after the origin time of the earthquake. So this is a P wave, how long it takes the P wave to get to, to some distance. This is time, this is distance. So let's go to 4,000 kilometers, okay? So if we're at 4,000 kilometers and we want to know when the P wave and the S wave arrive, so we go to 4,000 kilometers and we draw a line up here, and where we cross the P wave line is here, which is at about 6 minutes, and where we cross the S wave line is here, which is at about 12 minutes. So what this plot is telling us is that the P wave at 4,000 kilometers will arrive 6 minutes after the origin time, and the S wave 12 minutes after the origin time. That's what this plot is showing us. But the point is that when we're trying to locate the earthquake, we don't know the origin time. So the other piece of information that we can get from this plot is the difference between the S arrival and the P arrival. And that distance, that's this distance here in time, right? So this is between, whatever I said it was, 7 minutes, 6 minutes, and 12 minutes. So that's 6 minutes difference. There is only one distance when the difference between these two arrivals is 6 minutes. And that's right here. So when we're locating the earthquake, all we have is the seismograms. We don't know how far they are away. So we measure the S minus P time, 6 minutes. We come to here, we find a place on this plot where the blue and the red line are 6 minutes apart. That's right here, and then we measure off the distance. Yeah. It's the same, doesn't matter what the magnitude is. So this is all about travel time, and it doesn't matter how big the earthquake is, it takes the same time for the energy to travel. Other questions? Yeah. So the P wave travels at about twice the speed of the S wave. So yeah. That's right. That's why I say it's about half, not exactly half. Okay? Yeah. Yes, exactly right. Yeah, okay, good clarification there. Right, so if I was to remove these seismograms and just have this graph with the two axes and the two lines, that's a standard graph that you would use for every earthquake. And then for a given earthquake, you make your measurements, you come to this graph, you find where your S minus P time matches, you get your distance, and then you locate the earthquake. Okay, so you'll all be pleased to know that assignment number 3, actually, you will do this problem. Okay? So you'll be able to work through this, and I think that will help clarify it. That, now is not the time to do assignment 3 yet. Assignment 3 includes both a location problem and a magnitude problem. We haven't covered the magnitude yet. We'll do that next week, and that's when you should do assignment 3. Okay, so let's keep going. Okay, so this just shows, maybe I should have shown this already, this shows how the seismic energy travels through the Earth. So here's an earthquake starting. These are the P waves and the S waves traveling through the Earth's surface. You can see the P wave getting to this station, and then the S wave getting to this station, and the surface wave getting to this station. And so this just shows how the energy is traveling through the Earth. This is the animated version of what I drew on the blackboard. And this just shows the seismograms being built up as a function of time. Okay, so these are stations to a greater and greater distance. This is out to 90 degrees from the, or a bit more than 90 degrees from the epicenter. So of course the P wave arrived at this station last compared to all the others. This is the P wave. And the S wave arrived last. This is the S wave. And then these are the surface waves. When it comes to locating earthquakes, we just measure the S arrival time minus the P arrival. And you can see obviously that the S minus the P arrival time decreases as you get closer to the earthquake. And so that's the exact same figure that we were just talking about. Okay, everybody with me? Any more questions? All right, shall I show that again? Okay, all right. Okay, so now we've talked about waves traveling through the Earth's interior. You've seen these ray paths several times. I drew one on the blackboard right here. You've seen them in that cartoon, and now you see them also drawn out here. So again, here's this is showing an earthquake. It's shown here being at the North Pole, and then it shows the ray paths, how the energy travels out to a station at 20 degrees, 40 degrees, 60 degrees, 80 degrees, 100 degrees. Okay, and also energy traveling all the way through the Earth's core to the other side of the globe at 180 degrees. So the Earth's core, of course, has a solid iron inner core and then a liquid iron outer core. All right, and that's critical because another fundamental difference between P waves and S waves, we haven't talked about this, is that P waves can travel through a fluid, but S waves can't. It's pretty obvious why that would be, right? P waves, it's like a pressure wave. So the fact that you can hear my voice is because I'm transmitting a pressure wave that travels through air. You can think of air as being fluid. And so I'm creating this pressure wave where these particles are getting closer to one another and radiating out towards you. Now, if I was generating an S wave with my voice, that would be these particles moving from side to side. And a fluid can't hold that. So a fluid can't transmit a sideways motion because the particles would just shear past one another. So the point is that S waves cannot travel through fluids. That means that S waves cannot travel through the Earth's outer core. Only P waves can travel through the Earth's outer core. Okay? And so I guess actually this is just showing P waves and getting ahead of myself. So on the next slide it shows the S waves. But this is why there's a more complicated pattern to the arrivals that we have, is because of the fact that we have a core, first of all, which causes these ray paths to do strange things, and the inner core, the outer core rather, is fluid, preventing S waves from traveling through it. But you don't need to worry about these complexities. I just want you to have an understanding of how the energy travels through the Earth. So to come to the question that was asked earlier, why does the energy dive down into the Earth and then come back up to the surface? The answer to that is that the energy takes the shortest path. Okay? And so because the velocity of rock increases with pressure, so the velocity increases with depth. So it is faster for a P wave that's coming to a station at 40 degrees to dive down into the Earth, travel at a higher velocity down here, and then come back up to the surface, rather than traveling all the way across the surface of the Earth. It's the same problem when you're deciding to drive somewhere, and you have to decide, is it worth me going off over there to get to the highway, driving along the highway at 70 miles an hour, and then going from the highway, or do I just take the most direct route on surface streets? And if you're only going a short distance, it's faster to take a direct route on surface streets, even though they're slower. If you're going a greater distance, it makes more sense to take a longer path out to the highway, along the highway, and then back from the highway. It's exactly the same with the Earth. Okay? So that's why these ray paths bend down